Hi everyone, welcome to first in a series of videos tackling some past paper problems from the IB Standard Level AA course. This is a section B question, so extended response, a few different bits and bobs. It's a fairly straightforward one involving a quadratic, and we can already see we've got some root form here. We're asked about vertex form down here, so knowing the different forms of your quadratic and what that means and how it corresponds to the graph is going to be key to answering this question. So let's dive straight in. We've got a function. As I said, it's a quadratic. We've got a negative facing quadratic, and the following diagram shows it as f. Now the graph has intercepts p0 and q0. Those are here and here, and an intercept at 0, 12. So we're told where it crosses the axes. Now, first question says write down the value of p and q. As we know from IB problems, when it says write down, there should be a minimum of thinking. We're really just identifying a part of the problem that gives us this answer. And here it is up here, as I mentioned earlier, the root form of a quadratic. If we look at that closely, we can see that we're going to have 1 for q here on the x-axis and 3 or negative 3 for p there. This of course is because if I were to substitute the values of 1 or negative 3 into this quadratic, it's going to make one of the brackets 0 and therefore the whole thing 0, and that's how we get a root. Remembering that in general the root form is x minus alpha times x minus beta, where alpha and beta are our roots. We can have an a out front as well as a vertical stretch, but that doesn't affect the roots. So there's the write down part of the question. Very simple. P is negative 3, Q is 1. Okay, next says find the value of A. Now find, obviously not going to be as straightforward as a write down problem, but we should have most of the information we need here. Let's work on our function here, f of x, and let's just go ahead and multiply out these brackets. So x plus 3 times x minus 1, we do the firsts, we do the outsides, we do the insides, and we do the lasts. What that's going to allow us to do is just substitute in 0. We could have done this before expanding, I suppose, but nothing lost there. So 0 squared minus 0 plus 3 lots of 0 minus 3. So obviously these are all going to zero out. We're left with negative 3a. Now by substituting in x is 0, what we're doing is we're evaluating this function when x is 0, i.e. on the y-axis. Now we know that it should be crossing the y-axis just up here at 12, so we can now form this into an equation where negative 3a equals 12. Dividing through by negative 3 gives us that a is negative 4. Now that chimes in nicely with what I thought at the beginning. I mentioned this is a negative facing quadratic because it curves downwards like a sad face. That's going to give me a negative value to my lead coefficient here, a, because it makes the whole function negative and downward facing. So that seems not too bad, the value of a, negative 4. Okay, on to the next section. We have find the equation of the axis of symmetry of the graph. Well, this shouldn't be too tricky for us. There's a few different ways we can approach this here. First off, we do know the values of p and q. So this one from the last page was negative 3. This one is 1. Now, quadratic graphs are symmetrical about the axis of symmetry, hence its name. And therefore, this should be halfway between negative 3 and 1, which is going to be at negative 1. Of course, we turn that into an equation. It's got a line going through the x-axis at negative 1, so we get the equation x equals negative 1. There are a few other ways we could evaluate this. If we have a general quadratic written as ax squared plus bx plus c, which we were getting towards on the last page, then remember that the axis of symmetry is given by negative b over 2a. So we could have just substituted in there. But I think given that we've got both the roots, it's most convenient to just find halfway between them. and that just corresponds nicely to -1. Then we're asked to find the largest value of f. Well, I already know the x value here is -1, so all I need to do is do f of -1 to find what the corresponding y value is. Just flipping back to the previous page, it's probably, well, I mean, we can use any form to substitute in here, but why don't we go with the root form here, x plus 3 times x minus 1, remembering that a is of course -4, x plus 3, x minus 1, so I can now substitute in my -1, just taking care with the negatives here. Brackets are going to help us out, -1 minus 1, a little bit tricky. But we get -4 times 2 times -2. Two negatives are going to cancel. I'm left with 4 times 2 times 2, which is going to be 16. So I can go back to my graph and just make sure this sort of makes sense with what I'm expecting. The coordinates of the vertex here are therefore -1, 16. Well, just to the left of 0 and just above 12. So it's looking pretty good here. Next, back to the problem, we have the largest value of f done. So we've just got this last section where it says the function f can also be written as, and again, as I intimated at the beginning, this is our vertex form, or the completed square form, whatever you want to call it, and we need to find the value of h and k. Well, the beauty of the completed square form, or the vertex form, is that these coordinates up here, our -1 and our 16, directly tell us what h and k are going to be. So if we're asked to write it in the form of x minus h plus k, this form gives us that the vertex will be at h, k. Therefore, if our vertex is at -1, 16, then we have a h value of -1, a k value of 16, and that's just reading again straight off the vertex, so not too bad there. Now, if we perhaps didn't have the vertex, or if we'd like a different approach here, one of the things we can do is to work on this algebraically. So we could take our original vertex form here, it's very small. We can multiply this out, as I think we did earlier. X plus 3, x minus 1. Just reminding ourselves a little bit of FOIL. We get -4 times x squared, outsides, insides, and lasts. And we can multiply all this out to be -4x squared. X plus 3x gives me 2x, multiplied by -4 is going to be -8x, and then we get plus 12. And in order to turn things into the vertex form, we're going to complete the square. I think the first thing to do, I mean, we perhaps should have just left this out here, but I wanted to turn this into our general quadratic, ax squared plus bx plus c. We'll start by taking -4 out as a factor. Again, just going back a step really. X squared plus 2x minus 3, just get that the right way around. And then we look to complete the square by halving the b coefficient in here to give us x plus 1 all squared. Now the way I like to do these is I just, as an aside, I square out the bracket, reminding myself of course that when I square a bracket it's like having two brackets. I get x squared plus an x plus another x plus 1, giving me x squared plus 2x, which is what I wanted. Remember, that's what I'm trying to get here. But this also comes with a plus 1. Now, what I actually want to happen is I want it to have a -3. So I'm just going to need to go back and subtract 4 at this point, remembering that this whole thing is still under the bracket of -4. So we're good here. All we need to do is multiply out my -4s just to make sure we're back in the original form, which was -4 x plus 1 squared plus 16. And there you go, we can see these matching up. Our h value is in here as -1, or negative over -1 to make plus 1, and our k value is here at 16. And that's it, there's our question answered. A nice, fairly straightforward extended response question, but does require good knowledge of your forms of the quadratic. So we're using a general form sometimes, we're using our root form here, and we're using our completed square form. I think if you understand what those three forms mean in terms of where the graph crosses the axes here for the roots, and the maximum or minimum, the vertex point here, then this question shouldn't be too tricky. Thanks very much.